to ask questions. Bring a friend. Where I should go to, and so we need to go through those and so forth. So what we're going to go through is we're going to dissect as many questions as possible. I certainly don't think we're going to make it through the entire exam. For some of you, this is going to drive you crazy because you will take forever just to get through the first 10 questions. The reason for that is I'll just be jotting stuff down, and I'm notorious for jotting things in shorthand. And I'm messy. I use abbreviations, and by the second exam, you'll be kind of okay with it. I was kind of looking at the statistics and how I didn't want to cause anybody any more problems. I didn't want to cause some problems. So we're actually going to have 40 items on our test. And we'll have 60 minutes to complete them. And in the past, with other groups, I've had 50 multiple choice items for 60 minutes, so I think 40 is going to take pressure. It'll take some pressure off of you because some questions will probably go through pretty quickly, and ones will have a little bit more time to work on. So there'll be 40 items, and for this exam, they all will be multiple choice items. Today, as we go through, I'm going to go through a whole bunch of these early questions in just incredible detail. Please ask questions and yell at me and wave your hand. So I'm a little bit better now that I'm wired, but I'm still not very good at telling direction from where voices are coming from. So, and please ask questions, because if you have a question, guarantee 40% of the other people have it as well. So, okay, question number one, let's read that. And steroid hormones signal the cells what to do and when to do it. Fine, okay, I always tell students when you have the luxury of having a paper exam, and yes, there are some luxuries with paper exams, you bring a number 2 lead pencil, what the heck's a number 1 pencil? But bring a pencil. When you have the luxury, and now you can do it with some of the computer examination programs too, I want you to slow down a little bit and underline the automatic qualifiers in that statement. So the most important automatic qualifier right there is steroid. Steroid. Boy, that right there automatically sets the table for so many different things. What do you make steroid hormones from? What do you use to make steroid hormones? What's the backbone? Cholesterol, right? And cholesterol is incredibly hydrophobic lipophilic. And that physical chemistry makes a big difference in how we deal with steroid hormones. So when we say steroids, immediately start thinking, we've had these before previous classes, estrogen, testosterone, progesterone, aldosterone, cortisol. I will mention those hormones to you, but you do need to recognize, in the past I've learned that those were steroid hormones. And I won't go deep into some, we really have a lot of steroid hormones in the body, some of which you may not recognize, and I'm not going to go there. I'm just going to go very obvious. So if you have something that is hydrophobic, do you think it's going to be really transferable in the bloodstream? Is it water soluble? Your blood is water based. And anything that is hydrophobic, do you think it's going to have problems passing through the bloodstream all on its own? It's going to have big problems. So when the plasma is being transferred by plasma transport proteins. So it's catching a ride. So if I were to just kind of draw this, if this is some fluid flying by, here's a transport protein, and here's our steroid hormone. Catching a ride on that thing. How about passing through the membrane? Do steroid hormones, can they pass through the membrane or can't they? They can pass. Why? They're lipophilic. And this membrane bilayer, there's no problem. This thing's popping on. And it can easily go right through the membrane. So it passes through the membrane. Why? Because of its physical characteristics. If it passes through the membrane, does it need a membrane signal transduction pathway? No, if it goes through, it doesn't need that. Because membrane signal transduction pathways, those are necessary for those hormones and neurotransmitters that can't cross that membrane. So no second messenger signal transduction pathway. Doesn't need it. So, but once steroids get inside the cell, what happens then? Do they bind anything? Where do they bind? They bind some receptor, and depending on the hormone, sometimes the receptors are inside the cell, sometimes the receptors are inside the nucleus. But what do those receptor hormone complexes then do? They interact with the DNA to regulate transcription. Sometimes these turn on transcription. They literally bind the specific neurons on the DNA called response elements, and they're either going to turn on or turn off transcription. Let's say that this is turning it on, so it's going to make mRNA is going to be, you're going to transcribe mRNA, and then you're going to translate it into a protein. Well, that takes a little bit of time. So steroid actions, very often, they take a little bit of time. Why? Transcription, translation, making a protein. They have time to then process. Does that make sense? Okay, so that's some things to think about. I'm not suggesting you write all that down before you get to the choices, but always, when you read the stem, the first part, the setup for an item, slow yourself down, underline those automatic qualifiers, whether it says increase, decrease, suppress, augment, an alpha or a beta, steroid or peptide. Slow down and underline those automatic qualifiers. Because I'm sure you're like me and you're like other students I work with. You take an exam, you go, how did I miss that? Because I was going so fast, my eyes read something or didn't notice something that was just right there. And when you underline those automatic qualifiers, it slows you down and focuses your thinking. And that's a great habit to get into for a lot of different things. So, we know quite a few things about steroid hormones. So, let's say steroid hormones signal the cells what to do and when to do it by A, generating IP3. What do you think about that? No, why? That's generated with a second messenger pathway, isn't it? And we've already decided that these steroid hormones don't need a second messenger system. Now, very quickly, I'm going to just draw bare bones for, so here we have pt2, G protein. Here we have, so this will be bare bones for generating IP3. So the alpha subunit along with the GPP is going to activate. In this case, it's a catalytic enzyme, so it's a receptor, G protein, catalytic enzyme. In this case, it's phospholipase C. And what it's going to do is it's going to take a membrane phosphatidylinositol phospholipid, and it will generate inositol triphosphate and diacylglycerol. So this IP3, this part of choice A, it's actually generated in a membrane signal transduction process. So what's a big thing that IP3 does? There you go, I love it. Different cells have different storage decodes for calcium. Most cells store quite a bit in the pneumoplasmic reticulum. We usually think about skeletal muscle and cytoplasmic reticulum, but most cells, it's the pneumoplasmic reticulum, and it causes an increase in calcium. Diacylglycerol can actually interact with a peripheral protein to be acted on by protein kinase C. And the bottom line is calcium and protein kinase C will activate things because of their actions. So, yep, when we're talking about steroids, IP3 is not going to be involved because this is where IP3 is involved, right? Now, I gave you like 4 different ligands that utilize the IP3 pathway. And I told you there's more than 100 that utilize this pathway. But I told you alpha adrenergic receptors, angiotensin 2 receptors with this. I know I told about the gonadotropin releasing hormone, and I think maybe I told about thyroid releasing hormone. Those were on the list. And I put that there for a reason because there's something that, if you didn't make a connection with it when you took a previous physiology course, I want to just, any of you remember what, anybody remember what angiotensin 2 does to arterial smooth muscle? Strong vasoconstrictor, powerful vasoconstrictor. What's a smooth muscle? We haven't gone through this yet. But what a smooth muscle needs to contract? Calcium. So guess what? That vasoconstriction is providing the calcium to cause arterial vasoconstriction. Same thing with norepinephrine and epinephrine can each bind alpha adrenergic receptors. And in arterial smooth muscle, that leads to vasoconstriction. Those are some, we're going to be talking about those things very, very shortly. But, you've had some physiology before. You might not know why does angiotensin 2 cause vasoconstriction? Because it's linked to a membrane signal transduction pathway that causes this increase in calcium, and calcium helps drive the smooth muscle contraction process. Okay? So I know that's a little bit far afield. This next, so the steroid hormones, are they involved in inhibiting phosphodiesterase? No, phosphodiesterase is part of what signal transduction pathway? Yeah, the cyclic AMP adenylate cyclase pathway. So it schematically is very similar to this IP3 pathway. Once again, we have a receptor, a G protein complex. In this case, it's GS. The catalytic enzyme here is adenylate cyclase. So it will take ATP and convert it to cyclic AMP. Cyclic AMP will then activate protein kinase A, and that is going to lead to cellular actions. So it's the same type of scheme, but some different players. You know, that's what Rossi was learning. Same players, same positions, just different players. Now, you want to be able to control turning all of these off, and one of the ways you turn off this pathway is by simply degrading cyclic AMP with a straight chain AMP. And phosphodiesterase does that. Okay? So that's where this phosphodiesterase comes in. And I told you, and most of you probably haven't had a chance to do that tutorial yet. Anybody have a chance to do the tutorial? Didn't really think so. But the methylxanthines, and there's 3 big ones: caffeine, theophylline, theobromine. Caffeine often associated with coffee. Theophylline often associated with tea. Theobromine, dark chocolate. But most everybody, not most everybody, quite a few of you in this room will work in clinics where you'll have patients that you may be prescribing them theophylline. So there is a link to this pathway. So steroids have nothing to do. It's methylxanthines that inhibit them. So A and B aren't looking good at all. Still looking for an answer. So steroid hormone signal, so what's doing when you do it by regulating gene and protein expression? Well, okay, we know that's a correct response there. But let's just keep going. Steroid hormone signal to cells, what's doing when you do it by B, binding receptors on the membrane surface. What binds membrane surface receptors for hormones? Peptide hormones. And also neurotransmitters. Okay, but not steroid hormones, peptide hormones. So things like insulin, growth hormone, ACTH, TSH, so many things that you've heard of before that we're going to be talking about in the weeks to come. So, E, let's see where that fits. So, steroid hormone signal to cells, what to do, and what to do it by activating membrane-associated catalytic enzymes. That would be like phospholipase C and adenylate cyclase. Those are membrane-associated catalytic enzymes. They're part of second messenger membrane signal transduction pathways, and steroid hormones don't do that. So, peptide hormones and neurotransmitters and growth factors tend to operate in these sites. These aren't the only membrane signal transduction. Remember, insulin has its own signal transduction. You know, just pop this in real quick. So, with insulin, when it binds its receptor, how does it set off its pathway? That's right. This receptor right here, the insulin receptor, actually has a tyrosine kinase subunit that is turned off. It's turned off all the time until insulin binds that receptor. That activates this tyrosine kinase, and that allows specific tyrosine residues to be phosphorylated. The bottom line is other proteins can be phosphorylated. So that's the only example of tyrosine kinase membrane signal transduction I'm going to be talking about is via the insulin receptor. And insulin is so important because glycemic control is so important, and diabetes is so important. So, you know, there are different times throughout this course, but more importantly, the course to come where you have to know, okay, insulin's regulating this that leads to cellular actions. So quite different from steroids. And while we're here, peptide hormones, are they lipophilic or hydrophilic? They're hydrophilic. So can they move freely in the bloodstream? Absolutely. So no transport proteins, right? Can they cross the membrane? Obviously not. They're lipophobic. So it's kind of, and I bet most of you were there, think of these things kind of in a package. Kind of yin and yang. I gave you that table that on one side is peptide hormones and cytokines and growth factors. The other side, and neurotransmitters. The other thyroid hormones and steroid hormones. And boy, once you kind of understand a little bit about everything starts with the physical chemistry, everything else falls in place. And makes life a lot easier. So guess what? We finally got through question 1. But we're going to be using this stuff over and over again. Okay, so here's something quite different though. Number 2. We have a divalent anion, X for the negative charges. Intracellular concentration is 5 nanomolar, so we have X is minus, and it is 5. And outside, okay, we have a lot of X. It's 50. So we're going to start with an electrically neutral cell. It's at 0 millivolts. And the question just is, the divalent anion has an intracellular concentration 5 and extracellular concentration 50. If the membrane of an electrically neutral cell becomes permeable to X 2 minus only, what would the membrane potential become? So, yep, you can plug things in the Nernst equations, and there's reasons to do that. And remember, the Nernst equation is an estimate of the equilibrium potential for any ion. But just generically, what's going to happen? What's going to happen? This, if we just open up the membrane for this ion, are we going to see influx or efflux? Yep, it's going to influx. It's going to negative charge. So what's that going to do to the charge of the side cell? It's going to, yes, it's going to make it go down. It's going to be negative. The inside of that cell is going to become negative. Now, is this X 2 minus is going to just keep coming in until we completely obliterate the chemical concentration gradient? There's going to be some point where it stops coming in, right? And you still have a chemical concentration gradient. Why? Why will it stop? The negative repel. Pardon? The negative repel, exactly. Every ion has an equilibrium potential. The equilibrium potential, in this case, is when enough of this negatively charged X2 minus comes in that the interior becomes so electronegative it's going to, as you say, repel any more coming in. You'll still have a chemical concentration gradient going in that direction, but you're going to have an electrical gradient going in that direction, so you're going to be at an electrochemical equilibrium point, and guess what? That's called the equilibrium potential. So let's see what this question says. So what would the membrane become? It would become electropositive? Electronegative? Yes. Electrically neutral? No. So there's actually a lot of ways you can spin those types of questions, but just take a breath, draw a little picture, and just think your way through it, and count common sense works. It works. Okay, so when a previously depressed glucose concentration is returned to its normal range, which of the following occurs when the concentration is within its normal range? So we illustrated this yesterday. So let's say we have a glucose that is low. We have specialized sensor cells that their job is to only activate when glucose is low. So what cells are those sensors that recognize hypoglycemia or low plasma glucose? Yeah, pancreatic, so it's the pancreatic alpha cells. So those cells are constantly pumping, they're just like a thermostat. Thermostat is, it's constantly measuring temperature. It's on, but it's not activated until you move out of the temperature range. So this sensor, it's constantly monitoring glucose, and we'll see later it's actually monitoring glucose indirectly via insulin, but it's monitoring the glycemic status, and it sensed that plasma glucose was low. So what do pancreatic alpha cells do when they have hypoglycemia? Release what? I love it. Release the hormone glucagon. Is that a steroid or is that a peptide? It's a peptide. Okay. Actually, I think that comes up later. So glucagon is now going to go and impact whatever cells have the glucagon receptor. So every cell that has glucagon receptors are called effector cells. Glucagon will bind those effector cells, and for example, in the liver has glucagon receptors, and what does it do? It signals the liver, produce new glucose to put in the bloodstream, and your stored glycogen, those are really chains of glucose molecules. Break down your glycogen to release glucose, that's called glycogenolysis, and put it into the bloodstream. So the problem is not enough glucose in the bloodstream, and the liver is going to start releasing glucose. So the bottom line is, as more glucose goes into the bloodstream, once the glucose level is back to normal, that sensor turns off, and that's called negative feedback. Now this glucose is going to be restoring the plasma concentrations. The sensors will sense that, and this whole process turns off. Now that glucose is normal, the sensor will turn off, release the glucagon will turn off, the effector cells will turn off. And we can do the same thing if we have an elevated glucose and we need to bring it back down to normal. So let me look to see what the options are. Okay, so we have depressed glucose, and it's now been brought back up to range. This is how the body does it, which the following occurs when the concentration is within normal range. Hey, homeostatic sensor cells are activated. You like it? I'd say they're inactivated. Once it returns back to normal, those sensor cells are going to become inactivated. You wouldn't want to keep releasing glucagon. Positive feedback is activated. Well, negative feedback is really what's occurring, isn't it? Come on, let's see. Homeostatic effectors are inactivated. Yeah, because once we're back to normal, sensors turn off, glucagon release turns off, effector cells will turn off pretty quickly. Questions on that kind of thing? Okay, so I can do that for elevated glucose coming back down. I can do that for calcium. I can do that for sodium. We just put in different flavors and so forth. But this is just one half. What do you call it when we also have a sensor effector negative feedback loop if glucose is elevated? What do you call it when you can control the concentration of something, or the pressure, or the temperature, or pH of something, if it's too high, we get it back down to normal. If it's too low, we get it back up to normal. What do you call that when you have control in two different directions? Bidirectional control. So we were just looking at one of the limbs of bidirectional control. So we weren't really looking at bidirectional control, but by golly, we have that. We have that in normal, healthy person. Okay, which of the following would decrease? So there's an automatic qualifier. I would underline decrease. Decrease the simple diffusion. I would underline simple diffusion. That's an automatic qualifier. Of a substance passing through a membrane. So pixel diffusion is pretty straightforward. Surface area times diffusivity, and that is really limited solubility over the molecular weight of the substance times the difference of the concentration gradient all over the thickness of the area of diffusion. So we're looking for a decrease, something to decrease. So would increasing the surface area for diffusion actually decrease diffusion rate? No, it would increase it. So A is not looking good, right? A is working. So basically, if surface area, limit solubility, and concentration gradient, if any of those goes up, diffusion will go up. If molecular weight, thickness goes up, diffusion goes down. As I mentioned to you, be very, very comfortable with which of these factors are directly related to diffusion. Meaning, if it goes up, diffusion goes up. If that factor goes down, diffusion goes down. And be very comfortable which of these are inversely related. The inversely related ones are this size, molecular weight, and the thickness of the barrier for diffusion. When they go up, diffusion goes down. When they go down, diffusion goes up. So think direct and inverse, okay? So we're looking for something that will decrease. If we decrease the limit solubility of a substance, yeah, that will decrease diffusion, won't it? So B is looking very good. Decreasing the thickness of the barrier of diffusion. If we decrease the thickness of the barrier of diffusion, that would increase diffusion rate. So that's not good. Decreasing the molecular weight. Decreasing the molecular weight would actually speed up diffusion, so that's not looking good. Increasing the concentration gradient. If you increase the concentration gradient, that's going to increase diffusion rate. Okay, before we leave this, what is the driving force for simple diffusion? The concentration gradient. That's what drives it. These modify it, and this is a modifier too. The greater the concentration gradient, the greater the diffusion, that's the driving force. That's the driving force. So it looks like these are the only thing. Osmosis. Osmosis. So here we have a cell, and oops. Here we have membrane translocation channel proteins that will allow water to go in and out of the cell. And what are those water channels called? Aquaporins. And there's 6 different types of aquaporins, and in those 6 different aquaporin families, you're going to see that there's different children in different families. But many, not all cells in the body, have these aquaporins that allow water to pass back and forth, back and forth. But when we're just talking about osmosis, what we're talking about is movement of that water, movement of that water. And when it's moving through those channels, it's moving with, you think it's moving with diffusion-like kinetics, active transport-like kinetics, mediated transport-like kinetics. What's the difference? It's moving with simple diffusion-like kinetics because there's no carrier protein here. It's a channel. It's a channel. So water can just pass through it. So in most cells, you have enough of these channels that you never saturate. So osmosis involves the facilitated diffusion of water through aquaporins. Facilitated diffusion is if you have some type of carrier protein, right? So that's not right. Osmosis involves active transport of water, no movement of water down its chemical concentration gradient. Yes, when you think of solutions, solutions are made up of water molecules and solute molecules. And water will go from an area of high water concentration to an area of low water concentration. And I know some of you have been trained to think water is cold to an area of higher solute concentration. And that's fine. It's just the inverse way of saying it. It's just the inverse way of saying it. Okay. Here we have, so I mentioned that one illustration. Okay, here's a neuron, and here's where you have lightning gated channels, here's where you have voltage gated channels, here's where you have beta potentials, here's where you have action potentials. Make sure you know that very, very well, because there will be action potential questions on this exam, but we won't have questions about the mechanism of action potentials. But you do need to know where on those neurons those action potentials occur, and that's what there's a couple of different slides. Very important. So, looking at that neuron on the bottom, in which neural region are rated potentials generated in some? And sometimes instead of generated, I say initiated. So, same thing. So, looking at that, where do you see, and I can never draw neuron, it just always looks like some bizarre. Okay, something strange. So we have dendrites and we have cell body here. Here we have the axon helix, here's the axons, here's the synaptic terminals. So, where do you have graded potentials? Don't give me a letter, give me a name. Dendrites and cell body, right? So graded potentials up here, action potentials down here. Before we even go on, graded potentials are caused by what type of channel protein? Ligand-gated. And we'll lose up right there. So that's exactly right, Graded potentials are generated by ligand-gated proteins up there. What generates action potentials down here? Voltage-gated. You don't know, probably, by just having a command of that, you have the keys to the kingdom of understanding so much of fundamental neurology. You really do. You really, really do. There's a couple of important exceptions to that, but you know the general first. We'll talk about those exceptions later on. So, in which neural region are graded potentials generated in some? Which one? What's good here? The only one that's good to me is D, Z, region Z. What we're going to say now, there'll be a lot of questions on this exam, and I think there's some questions coming up here, where, and this will be the case throughout your program here, on your national board exam. You're going to be told about a drug or a process that you don't know anything about. But they will tell channels. There. So once again, Z. Oh, Z's getting kind of popular here. So what we're going to say, place them there, won't do a thing. You place them here, will do a lot of things. Yes? Well, yes, yes, they can. Yes, they can. So unfortunately, there is some, but that is an and, generated and some. So both of those conditions have to be met. No, they're generated or initiated in the dendrites and cell body. But I agree with you totally that they are some there. So whenever you see an and, you need to be both conditions. If it was an or, I know, that's a different question. And that's one that I hope that I never write because it's splitting to me. I split hairs, but yeah, I don't want to get that many splittings. That's
So with that one, you'll still be in the dendrites. So the dendrites also get some potential? Okay.
Yes, dendrites and cell body both. Well, for some, dendrites, cell body, inherit the axon hillock. They're going to, the axon hillock really gets the impact of all that summation. That's where the impact of summation is evidenced. Thank you for the question. So, new information to apply. Students hate these, but yes. Or 7? Oh, I'm sorry, it's V, it's Z. So, what region is not affected? Well, it's the region that has no voltage-gated sodium channels, and the only region that doesn't. Y, X, W, they do. It is Z.
So why? The axon hillock has voltage or sodium channels?
The axon hillock definitely has voltage-gated sodium channels. Yes. From this point on, the axon hillock is like right here. Voltage-gated sodium potassium channels, and then we're going to see voltage-gated calcium channels down here. And actually, you're going to get a slide coming up on neuromodulation that will make things more crystal clear because we'll delve into that with a lot more specificity coming up. Any more? Okay, so yes. The axon hillock is where you have the very first generation of the action potential. That is absolutely correct. Yep. So it's braided here. It's action potentials in there. Does that kind of make sense to you? You can't see where you are. You can't see that. Yeah. Pardon, say that again? Yes, exactly. You need to, yesterday when I showed the picture of the human threshold, those braided potentials are what's driving you closer and closer to the threshold. The braided potentials are generated up in the dendrites and cell body. They're generated up there. That is what's driving the axon hillock closer and closer to the threshold. That's the first place. And that's how we know how to generate action. They receive the summation. They receive the summation actually. Because they don't have one thing. Well, okay, there are some neurons that do have a one mediated, but nothing like that. They receive the results of the summation. In actuality, that's what we do. Now I know that's a splitting genotype thing, but I try not to go too anal on that, but I know students always say, well, when you get to a point where you're actually trying to see the student understanding that, it's like, oh, this person's got a problem for language. So, okay. Inotropic glutamate receptors, oh my gosh, we haven't talked about that, this is okay, are ligand-gated ion plasma membrane channel proteins. Okay, so these receptors are, they have a receptor site, they're in the membrane, they're operated by that ligand binding it, and these activate and open when bound by the neurotransmitter glutamate. So when glutamate binds that receptor, it opens the channel. For one type of inotropic glutamate receptor, the AMPA receptors, and I did throw in, which incidentally has nothing to do with cyclic AMP. When you see that AMP, I don't want you to think it has anything to do with cyclic AMP or AMP. It's nothing to do with that, so don't let that worry. The primary ionic movement through the open channel is sodium, so that's primarily a sodium channel. So before we even go on, if we have a resting membrane, tell me, what's a good resting membrane potential for this one? It's a neuron. Pardon me? Minus 70, that's a good one. Minus 70 is a good one for a medium-sized neuron. It's resting at minus 70. Glutamate binds its receptor on this ligand-gated channel protein, and this allows sodium movement. What's going to happen? What is sodium going to do? Go in and go out of that cell. Go in. Exactly. You know this, that you have 10 times more sodium outside the cell than inside the cell, so when this channel protein opens, you didn't even know anything about this channel protein. But you know that it opens and allows in the presence of glutamate, which is a neurotransmitter for certain neurons, and you know that it's primarily selected for sodium. So, just having that information, what's going to happen to the membrane potential? It's going to become more positive. Yes, it's going to depolarize, won't it? So, that's going to be the result. It's going to go toward the equilibrium potential for sodium, which is what? 61. Plus 61. So, that's the direction that membrane is going to go. So, you tell me, I don't even remember where this question is going, but you tell me, let's say we have a whole bunch of these glutamate ligand-gated receptor channel proteins here, and this membrane is all depolarizing. So all of these gradient potentials are being summed and they're traveling toward the axon hillock. Do you think that's driving the hillock toward threshold, or is it driving the hillock away from threshold? This is toward. You bet. This is making, it's depolarizing. So, if this thing is resting at minus 70, maybe you only need to get to a minus 50. So this depolarization wave is going to go to the axon hillock. Guess what? That'll probably turn on that neuron. So you can say that glutamate looks to be an excitatory stimulus, doesn't it? And that's exactly what it is in the central nervous system. It's an excitatory neurotransmitter. So are you kind of making sense? Okay, so let's take a look at the question. Given the above information, where will these channel proteins be located on the neuron? Z once again.
automatic qualifier. You'll be seeing questions with similar, you'll see questions with different. And when you have like a similar, or I circle those, I don't underline them, man, I circle them. So we're comparing facilitated diffusion. Well, okay, the way I draw simple diffusion is this way. This is comparing facilitated. Simple. That's the way that I've drawn simple and facilitated, okay? So facilitated diffusion is similar to simple diffusion in that both. So boy, if you can, write an equation, draw a little picture, you know, these only take you about 5 seconds to do, and really, it activates another area of your brain to help keep you on track. Okay, facilitated diffusion and simple diffusion. Well, you know, before I even go on, we'll be talking about this in just a couple of minutes. We have passive processes, simple diffusion, and facilitated diffusion. And then we have active processes. We have primary active transport. We have secondary active transport. And within this, we can have co-transport. We can have counter transport. Okay. So before we even get to this question, if someone were to ask you, what's the biggest difference, give me 2 big differences between passive transport and active transport.
Passive doesn't use
ATP. Which one uses ATP? Active. So that's, active uses ATP, passive does not. Where does passive get its energy to do its job? Concentration gradient. Gradients drive physiological processes. So, what's another thing? The direction it's going. These passive have to go from an area of high concentration to an area of low concentration. These go from an area of low to high. So those are the two things I would definitely no ATP. Yes, ATP. And you know, this is going from high to low, this is going from low to high. Okay? So facilitated diffusion is similar to simple diffusion in that both A, utilize ATP directly. Neither of them do. So that's double wrong. B, both are passive transport processes. Yes, they both are. So let's see what's wrong with C and D. So C, require a membrane translocation protein. Actually, neither of them do. Facilitated means a transport protein. Remember, translocation is a channel protein. Neither. Now, even if that said require a membrane transport protein, that would just be facilitated, wouldn't it? Okay. Transports electrically neutral molecules across the membrane. Electrically neutral molecules are like these guys. They're lipophilic. They go across by themselves, don't they? So, and that's an interesting one because that would be true for simple diffusion. Remember, for facilitated diffusion, that's something where we have a concentration gradient, but this molecule can't cross the membrane because it is hydrophilic lipophobic. So D would actually be true for simple, but not for facilitated. So there's a differentiation there. E, allows the transport of substance to move against its chemical concentration gradient. That'd be for active and not for these passive processes. What do you think? Everything's okay? Okay. Which of the following statements is untrue regarding fluid volumes in compartments in a typical healthy person? So, and just make sure total body water volume is what percentage of total body weight?
60.
That's 60% of body weight, and intracellular fluid volume is 40%, and extracellular fluid volume is 20% of body weight. And the other way of looking at that is that intracellular fluid volume is 2/3 of total body water, and extracellular fluid volume is 1/3. So either way you do it, it works out the same. It works out the same.
Is there not more in extracellular?
Pardon me?
Is there not more in extracellular? Oh.
Yeah, it's intracellular is twice as much. Okay. So, A, we're looking for something true, so the automatic qualifier is true here. A, twice as much fluid is outside of cells than inside of cells. You're happy we had this review, right?
Yeah, I had it backwards.
See? Hey, guaranteed 30% of, before we start doing reviews, a third of the class constantly use that. Once we start doing reviews, it almost drops to zero. And I mean these dissections. So A is wrong because it's only half. Is it? Water accounts for 70% of a person's body weight. What do you think? It's much closer to 60. Much closer to 60. An 80 kilogram person would have approximately 16 liters of plasma. So let's kind of figure this out for somebody who's 80 kilograms for their total body water, so times 0.6. This person would have about, that it is 80 kilograms, 48 liters of total body water. So 2/3 of that would be intracellular fluid, 1/3 of that would be extracellular fluid. So that would look to me like 16 liters and 32 liters, okay? And extracellular fluid you can break into plasma, and you can break it into interstitial fluid. And you have almost, not quite, almost 4 times more interstitial fluid than plasma. So you can break that down even more. So an 80 kilogram person would have approximately 16 liters of plasma, while that person would have 16 liters of extracellular fluid. So they can't have 16 liters of plasma.
What's the approximate percentage of plasma? Or did we not learn that?
We did. For a 70 kilogram person, it's 3 liters of plasma, 11 liters of interstitial fluid. That I did give you.
Okay.
So, that's a little bit less, that's like 3.5 to 1 ratio.
Okay.
So it's close to that, a little bit off. But just know that you have close to 4 times more interstitial fluid than plasma.
Yeah.
That will get you there every time. That's the rule of thumb. Now 13, 14, 15, this kind of relies on you remembering some things from courses that you've taken in the past. So before we even look at that, when you have a metabolically active cell,
What was the answer called?
pardon me?
What was the answer that was?
Oh, I guess we didn't get down to E. So plasma and interstitial fluid volumes combined are half of the interstitial fluid. Yeah, that's the case no matter what. Oh, I guess we didn't look at E. Interstitial fluid volume is 2 times greater than intracellular. No, it's nowhere close to that. Nowhere close to that. Sorry. So, when you have cells that are,
I love E.
the correct answer is E. Okay?
Switched around and it's okay. Because I was like, wait a minute.
What?
Okay. When you were reading it, you just switched around. The sentences, but.
Okay. So, when you have metabolism going on to generate ATP, are you consuming oxygen or are you generating oxygen? You're consuming it. What are you producing? CO2. So the more active a cell is, the more CO2 it's producing and the more oxygen it's consuming. Okay? And in looking at this, I probably wouldn't do this type of question, but there is something that is close to this, so I want to go over it. So what those dots are CO2. And you can see that there's a small amount of CO2 around each of these cells. It's the same concentration outside. So if you look at A, you see a lot of CO2. You look at C, you see very little CO2. So, generally speaking, which cell do you think is more metabolically active? A, it's producing more CO2. Without even looking at the rest of this, which one do you think has a greater oxygen demand? A, if you're producing a lot of CO2, it means you need a lot of oxygen, okay? And remember, the simple diffusion with oxygen and CO2, it's so elegant. Whatever the cell needs, it gets. So, without looking at these things, if that's CO2, which cell, A, B, or C, would have the greatest oxygen diffusion rate? It's the cell that needs the most oxygen, right? And that is which one? A. That's it. That's it. Use your common sense, take a breath, and you get these.
So for 14, it would be C because it's the lowest that we're looking for there, correct?
Yes, but.
For 14?
Well, we're gonna go through these, so.
Oh, we thought you were answering the question, right? So that's.
No, so which cell is most metabolically active? A, right? Which cell would have the lowest oxygen diffusion? I agree. Which cell has the highest CO2 diffusion rate? A. Absolutely. Do look at those to see if you're comfortable with them. Okay, so let's compare facilitated diffusion to secondary active transport. So, I'm sorry for those of you right here, you're not going to be able to see. So stand up, take a look at my magnificent artwork. Down again. So secondary active transport, I can draw it in a couple of ways, but let's say it's this. X is what's really coming in, and that would be an example of secondary active transport. We're looking at how they're similar. So here's facilitated diffusion. Here's an example of secondary active transport. How are they similar? Circle that similar. Both of these, do they show selectivity? Selectivity would be, are these transport proteins selective in what they bring across?
Yes.
Absolutely. So they definitely share selectivity. Okay, at least one molecule is moving against its concentration gradient. That's the case here with secondary active transport, but that's not the case with facilitated diffusion, is it? So B's not looking good at all. C, they both involve membrane transport proteins, absolutely. '17, phosphodiesterase. Phosphodiesterase, talked about that right here. Phosphodiesterase assists in the regulation of signal transduction processes that utilize. We're going to cut to the chase. D, adenylate cyclase. 18, the internal milieu or the internal environment includes the internal environment. This turns people around, so it's just something you have to memorize and know this fact. Internal environment is your extracellular fluid. And what makes up your extracellular fluid? Plasma and interstitial fluid. So the correct answer there is D. 19. Sympathetic stimulation to mini arterioles activate a membrane signal transduction mechanism that results in increased cytosolic calcium. Calcium calmodulin binding, arteriolar smooth muscle contraction, and vasoconstriction. Applying this information, sympathetic stimulation to arterial smooth muscle results in, so what is a second messenger signal transduction pathway that interacts with norepinephrine and epinephrine, which those are the sympathetic ligands, and generates calcium. The IP3 pathway is so applying this information, sympathetic stimulation to arterial smooth muscle results in cyclic AMP. Wrong pathway, right? No. Activation of the GQ protein, that is found in the IP3 calcium pathway, isn't it? Activation of adenylate cyclase and alpha GT subunit, that's this pathway down here. So if you really know those pathways and what goes with each, you'll do very, very well. And really, we're not going to get to it obviously, but question 34. Let's turn to 34. We're going to come back and check out because there's a few questions coming up I really want to do. But 34 is asking you to think about what are the elements in this pathway and the sequence. So I always have these type of progression statements on every exam for different processes to know what goes together and if you understand them sequentially. So that kind of goes with what we were just talking about. Let's go to 20. Temporal summation differs from spatial summation. So what part of neuron do we see temporal and spatial summation? Dendrites and cell body, and we see that because of what type of translocation channel proteins? Ligand. Very, very good. So temporal summation differs. I circle differ from spatial summation in that temporal summation, A, occurs with action potentials. You know that even since we didn't even talk about that, when we were talking about graded potentials, I told you, well, this won't happen with action potentials. And then I talked about it again yesterday, so A's wrong, never. B, temporal summation differs from spatial summation in that temporal summation occurs with graded potentials. Well, guess what? Both. Temporal and spatial both involve graded potentials, so that's not a differ. That's not a differ at all. There has to be something a little bit better. Temporal summation utilizes ligand-gated ion channels. Both do. So that's not a differentiation. Temporal summation requires a single presynaptic neuron. That's true. Spatial, you need two or more firing at the same time. Temporal is one neuron firing sequentially. So D's looking the best. And I should mention, I haven't mentioned before, all of my exams, the questions are, and this is common in all healthcare programs, identify the best answer. And when you get into clinical medicine, you're going to be given a whole lot of items where there's 2, 3, 4 correct answers, but there's one that's best. And so this kind of gets you thinking about that. C, temporal summation has an absolute refractory period, but not a relative. No, that's a property of action potentials. Remember, graded potentials don't have any refractory periods whatsoever. That's what makes summation possible, not having refractory periods. Okay, 21, when plasma pH becomes either elevated or depressed, several mechanisms in the body return pH back to its normal range. This is an example of bidirectional control. I see a lot of heads going up and down, yes. Juxtacrine, autocrine, and paracrine, you have no questions on that because you didn't get that sheet from me, the problem with my drive that can't use it here because it blocks. C, homeostatic regulation. The correct answer there is E. So that's the question that I would give it to you in that format. Okay, so insulin and estrogen are similar. Okay, so insulin is that a steroid or a peptide hormone? It's a peptide. And estrogen, is that a steroid or a peptide? It's a steroid. So you know there's some things different, but there's some things similar. Okay, so insulin and estrogen are similar in that both A, regulate cell function. Yeah, okay, that's a generic, but I'd buy it. They both utilize membrane signal transduction processes. That's just insulin, but not steroids, right? They both bind membrane surface receptors. That's just insulin and not estrogen. Okay, what I'm going to do now is turn to your back page. I don't want you to mark the correct answers. I know a lot of you have already gone through these. I'm just going to put down what the correct responses are. And I don't want you to just circle it right away because that changes your psychology. If you haven't gone through these, go through them and then look at the correct answers. So 23, D. 24, D. 25, E. 26, B. 27, D. 28, C. 29, E. 30, C. 31, B. 32, D. 33, B.
What was that?
33 is B. 34 is D. 35 is A. I hope you didn't put them right on. I hope you didn't put them on the question. Okay, so I know a lot of you have already gone through these. For those questions we haven't gone through, are there any you want to ask me about right now? So before we take off, you got to tell me where. So I can be here for an hour or so on Sunday, from late Sunday afternoon or Sunday evening. Does anybody want to? And I will be here. I can come here. I probably won't get here until 5:15, 5:30 on Monday night, and I can stay for about an hour and a half. So I'm thinking 5:30 to 7 on Monday night. I can be someplace, and then if anybody would want, and if anybody and their friend want to meet on Sunday, I can be here. But you got to tell me where, and you got to tell me if you want me to be here. So Sunday night, how many of you think you might have questions? Don't? Okay, we have at least 3, and that's enough. So I've been told that we have marker boards in the gross lab, and Dr. Burton said I certainly can use that. I don't know, that's in the building just right.
Kruger Center.
Science building.
Yes.
What's the name of that building?
Kruger.
Okay. But I know I can't get into that building.
We have a key.
Okay.
Some of us have a key.
So is 5 to 6 okay on Sunday?
Yeah.
Is 5 to 6 okay? Okay, so 5 to 6. I'll meet you at the front. Well, which door?
So the building will be open.
Okay, the building.
will be open.
Okay, so I'll just go. Where's the gross lab?
It's downstairs, all the way east.
It's
Okay.
157, room
157.
157.
157.
Yeah. Literally last time.
Okay, so Sunday at 5 to 6, and then room 157 on Monday from.
I'm like, oh, this makes sense.
Try to get here soon, but I'll stay here until 7 o'clock.
Yeah.
Okay?
Look at my gosh,
Good luck. Have a good weekend study.
Dr. Crouch, What time on Monday did you say?
On Sunday, Sunday will be from 5 to 6.
And Monday, did you
And
say?
then I'm gonna email this, Monday will be 5:30 to 7.
5:37, thank you. Thank you.
No, actually, there's a new package here. So this one opens up the battery side.
Okay, overall, I have to ask you, did that make some of you more comfortable?
Absolutely.
Okay, okay, good. Because sometimes these make people uncomfortable, and so, because they go, oh, Lord, I didn't know I did. Well, long term, a lot of stuff.
Have you charged it yet?
No. Why?
It'll work right now, but so since these are nickel cadmium batteries, they have to be charged all the way up, discharged all the way up 3 times.
It worked last night when I tried
Right,
it.
it should work. It should work, but to make the battery last as long as possible, you have to charge it and discharge it all the way. It's not a lithium ion, which it can be at
So
any
as long
time.
as it's not out, it's not going to make a difference in the charge.
Oh no, it'll charge. Just to like break in the battery, you're supposed to charge it all the way for 16 hours, and then discharge it all the way, and then charge it again for 16 hours, 3 times. Just like on the second charge. Almost.
And this was
I
going
meant like
into exercise.
almost 15 hours on that charge.
I want to make sure I didn't left turn on something.
Yeah, it's